Have you ever dropped your phone and watched in slow motion as it hurtles towards the ground? Or maybe you've stumbled and felt that undeniable pull bringing you back down to earth. That invisible force, my friends, is gravity. It's the ultimate cosmic glue, the silent director of the universe's grand performance. And today, we're going to dive deep into why we can't escape its grip. So, what exactly is gravity? For centuries, people just accepted it as a fact of life. Apples fall from trees. Things fall down, not up. Simple, right? Well, not exactly. It took a genius named Isaac Newton sitting under an apple tree so the story goes to start putting the pieces together. In the 17th century, Newton proposed his law of universal gravitation. He realized that the same force pulling that apple to the ground was also the force keeping the moon in orbit around the Earth, and the Earth in orbit around the sun. Newton's big idea was that every object with mass in the universe pulls on every other object. The more mass an object has, the stronger its gravitational pull. And the farther away you are from it, the weaker that pull becomes. Think of it like a cosmic magnet. Our planet, Earth, is a giant ball of rock and metal with a whole lot of mass. That's why it has such a strong gravitational pull on everything near it, including you, me, and that phone you just dropped. This pull is what gives us weight. Your weight isn't a measure of how much stuff is in you. That's your mass. Your weight is actually the force of gravity pulling your mass down. That's why astronauts are weightless in space. They still have the same mass, but they're far enough from Earth that its gravitational pull is much, much weaker. Newton's laws worked brilliantly. They allowed us to predict the motion of planets, calculate the tides, and send rockets into space. For over 200 years, it was the definitive explanation for gravity. But then, another genius came along and turned everything on its head. His name was Albert Einstein. Einstein wasn't satisfied with Newton's explanation. He wondered, how does gravity know how to act instantly across vast distances of empty space? How does the sun tell the Earth to stay in orbit? He proposed a revolutionary new idea in his theory of general relativity. Picture a stretched out rubber sheet. Now, place a heavy bowling ball in the center. What happens? The sheet curves and dips around the ball. Now, if you roll a small marble nearby, it won't travel in a straight line. Instead, it will follow the curve created by the bowling ball. According to Einstein, that's exactly what gravity is. Space-time isn't empty. It's a flexible, four-dimensional fabric. Massive objects, like stars and planets, don't pull on other objects from a distance. Instead, they bend and warp the very fabric of space-time around them. And what we feel as gravity is simply us moving along these curves. So, the Earth isn't being pulled by the sun, it's following the straightest possible path through the curved space-time created by the sun's immense. Mind-bending, isn't it? It means you're not being pulled down to your chair right now. The mass of the Earth is bending space-time, and your chair is just preventing you from following that curve straight to the center of the planet. Einstein's theory has been tested and confirmed time and time again. One of the most famous confirmations was observing how starlight bends as it passes us by the sun during a solar eclipse, exactly as Einstein predicted. His theory also predicted the existence of black holes, objects so massive and dense that they warp spacetime to such an extreme degree that nothing, not even light, can escape their gravitational grip. It's the ultimate cosmic trap. More recently, in 2015, scientists made another groundbreaking discovery that confirmed Einstein's theory, gravitational waves. Remember our rubber sheet analogy? If you drop two bowling balls and they spiral into each other, they would create ripples spreading out across the sheet. Gravitational waves are those ripples in spacetime created by cataclysmic events like two black holes colliding. Detecting these unimaginably tiny ripples, which stretched and squeezed spacetime on Earth by less than the width of an atom, was one of the greatest scientific achievements of our time. It opened a brand new window to the universe, allowing us to hear the cosmos in a way we never could before. So, the big question remains, can we escape gravity? The simple answer is no, not really. Gravity's reach is infinite. Even in the deepest, darkest voids of intergalactic space, the faint gravitational tug of distant galaxies is still there. You can never truly get to a place with zero gravity. However, we can overcome it. Think about a rocket launching into space. It's not escaping gravity. It's fighting it and winning, at least temporarily, to break free from Earth's gravitational hold and travel to other planets. A spacecraft needs to reach what's called escape velocity. For Earth, that's about 25,000 miles per hour, or 11.2 kilometers per second. At that speed, you have enough momentum to coast away from the planet without falling back down. Even though Earth's gravity is still pulling on you, getting weaker and weaker as you travel farther away. Even when astronauts are floating around the International Space Station, they aren't in a zero-gravity environment. The space station is only about 250 miles up, where Earth's gravity is still about 90% as strong as it is on the surface. So why are they weightless? Because they are in a constant state of freefall. The station and everything in it are continuously falling towards Earth, but they are also moving sideways at such a high speed, about 17,500 miles per hour, that they constantly miss it. They fall around the Earth. It's like throwing a ball so hard that its path curves around the entire planet before it hits the ground. That's what an orbit is. A perpetual state of falling and missing. Gravity is more than just a force that keeps our feet on the ground. It's the grand architect of the cosmos. It's what pulled together the primordial gas and dust to form the first stars and galaxies. It dictates the orbits of planets, the dance of moons, and the fiery life and death of stars. Without gravity, the universe as we know it would be a cold, chaotic, and formless soup of particles. There would be no stars, no planets, and no life. But scientists are still trying to understand it fully. Gravity is weirdly weak compared to the other fundamental forces of nature, like electromagnetism. A simple fridge magnet can defy the gravitational pull of the entire planet to hold up a piece of paper. Why is gravity so feeble? And how does it fit in with the bizarre world of quantum mechanics? The physics of the very small. Physicists are hunting for a theory of everything that would unite gravity with the other forces? Perhaps through ideas like string theory or quantum gravity. The answer to these questions could unlock even deeper secrets about the nature of our reality. So, the next time you drop something, take a moment to appreciate the incredible, invisible force at play. You're not just witnessing a clumsy accident, you're seeing a fundamental law of the universe in action. You're experiencing a warp in the fabric of space-time, a cosmic dance choreographed by mass and energy that began with the Big Bang itself. Gravity holds our world, our solar system, and our galaxy together. It's the reason we have a place to call home. We can't escape its grip, and honestly, we wouldn't want to. Thanks for joining me on this journey through space. If you enjoyed this and want to explore more cosmic mysteries, don't forget to like this video and subscribe to the channel. Let me know in the comments what other universal forces you'd like to learn about next. See you in the next one!